Normal form games are natural model to describe simultaneous action games, such as rock, paper, scissors. A game is described by a pair. The first element of the pair is the mechanism of the game, describing the rules of the interaction. The second element is the strategy of the player, describing the behavior of the players during the play. In the normal form, the game mechanism is described by means of a tabular representation, in which the rows are controlled by player 1 and the columns by player 2. With more than 2 players, we have a tensor in place of a tabular representation. We need to assign a different label to each action of the players. We start with player 1 and we assign the labels C and D. C is the label of the first row, that is the first action of player 1. D is the label of the second action of that player. We focus on player 2, whose actions are C and D. Each combination of actions of player 1 and player 2, for instance C for player 1 and D for player 2, identifies an outcome of the game. That is, in a cell we have in principle a different outcome. Players have preferences over the outcomes, and these preferences are expressed in terms of utility. The larger the utility, the better for the players. Usually, in the normal form representation, outcomes are omitted, and in their place we report the utilities of the players, such as in each cell the first number is the utility of player 1, while the second number is the utility of player 2. Now we are ready to provide a formal model. A normal form game is a tuple and a U, where A is, as usual, the set of players. A is the set of players' spaces of actions, where A1 is the space of actions of player 1, and A2 is the space of actions of player 2. Each space of action is a set, finite or not, of actions of a player. U is a set of utility functions for the player, where U1 is the utility function of player 1 and U2 is the utility function of player 2. The utility function of each player returns a real number for each combination of actions of the players. Now we focus on the strategies. Recall that while the game mechanism defines the rules of the interaction, strategies define the behavior of the players during the play. Consider the game in the picture that is known as the prisoner dilemma. The strategy of a player, denoted with sigma, is a probability distribution over the actions. We denote with delta the simplex, corresponding to the probability distribution defined over the space of actions. An example of strategies is, for instance, for player 1, to play C with a probability of 1/3 and action D with a probability of 2/3. For player 2, to play 1 alpha uniformly over C and D. When a strategy does not prescribe that an action is played with a probability of 1, it is called mixed. Instead, when a strategy puts 1 over the probability of an action, it is called pure. The combination of a strategy per player, in the picture sigma 1, sigma 2, is commonly denoted with sigma without any pedix, and it is called strategy profile. In general, a profile is composed of 1 element per player. We try to represent the strategy space of the players. Focus on player 1. We have sigma 1c, that is the probability that player 1 plays C. This value is in the range 0, 1. And we have sigma 1d, that is the probability that player 1 plays D. Also in this case, the value is in the range 0, 1. The same for player 2, with sigma 2c and sigma 2d. However, the strategy space of a player, in this case, it is not the entire square, given that the two probabilities are not free. Indeed, the sum of the two probabilities of one player must be 1, otherwise the strategy is not a probability distribution. Therefore, the strategy space of the players is the red line reported in the slide, also called, as said before, simplex. If you want to represent the strategy profile space, we need to make the Cartesian product of the strategy spaces of the players. In the case reported in the slides, the strategy space of each player is a 0-1 line. Therefore, the Cartesian product is a box, as reported in the slide. That is, any point in the box corresponds to a strategy profile. We focus on the utilities of the players. Given a pure strategy of the players, their utility are those corresponding to the outcome the players reach. For instance, in the picture, player 1 plays action D with probability 1, while player 2 plays action C with probability 1. Thus, the player utilities are 4 for player 1 and 0 for player 2. The question is, what does happen when players play mixed strategies, randomizing over the actions? As it happens in the picture, where player 1 plays 1/3 over C and 2/3 over D, while player 2 plays uniformly over her action. First, we need to introduce the notion of lottery. A lottery is a probability distribution over the outcomes. In the case reported in the slide, we have that the strategy profile induces the following lottery: 1/6 on CC, 1/6 on CD, 1/3 on DC, and 1/3 on DD. Since we have a probability distribution over the outcomes, we cannot speak of a utility, but expected utility. The expected utility of player 1 will be 1/6 multiplied by the utility for player 1 from CC, 1/6 multiplied by the utility for player 1 from CD, and so on. The result is 13/6. When we consider the strategies of the players as variables, the expected utility function is a function whose arguments are the strategies themselves. Such a function is a polynomial in the strategies of the player, whose maximum degree is equal to the number of players. To conclude, we report an example with 3 players. Suppose that we have 3 players and that each player has 2 havable actions, say A, B. Player 1 controls the rows, player 2 controls the columns, while player 3 controls the tables. Suppose that player 3 plays a mixed strategy, 1/3 over A and 2/3 over B. Suppose instead that the strategies of player 1 and 2 are free. What we can do is to remove player 3, computing an expectation the utilities of player 1 and 2, where the expectation is computed with respect to the strategy of player 3. Therefore, we need to do a convex combination of the first table using a parameter of 1/3 with the second table using a parameter of 2/3, and obtaining a game in which only player 1 and player 2 can decide their strategies. The resulting game is that reported in the slide. Finally, let us remark that the nature player may be present. In that case, the normal form should be found considering that the nature player is a standard player, and subsequently removing it, computing the utilities of the players in expectation with respect to the strategy of the nature player.